Okay, hello. We're going to go ahead and get started. Today we're going to dive into wastewater treatment. Today we'll be talking a lot about, not dive into wastewater, that'd be bad. We'll explain how bad that would be at some point. But we're gonna talk about the motivation largely, and then the regulatory framework with which we use to achieve such motivations. So today we're gonna begin taking a look at what is in wastewater, why do we care about it. We'll touch on a few things that we've taken a look at before, and we'll also cover primary treatment. So this is kind of the regulatory side and the beginnings of wastewater treatment. Then most of wastewater treatment that is distinct from what else we've learned so far will be the biological component. We're going to use microbes to eat the stuff, and that's very helpful for us, as we'll see, because we can change something that's dissolved. We have no way to grab it from the water, and we can convert that into a bacterial cell, which is an object. And then we can take that object and filter it or let it aggregate into larger clumps and settle it. So if we can convert the dissolved stuff into some physical object that is larger particles, that's quite convenient. So that's largely what we'll be talking about as we get into the biological treatment for wastewater. Okay, so we take a look at this slide already once in the context for chlorination. I'm bringing it back up here because we also know that wastewater treatment kind of coincides with the same improvements in infrastructure, and overall our treatment of wastewater is a major part of why we no longer have so many waterborne diseases, where we have the two barriers to the fecal-oral route of transmission. Typhoid fever is one of those pathogens that is transmitted in such a manner. So even though chlorination began and became popular somewhere around 1900, 1910, took some time before that was fully implemented, and of course our wastewater infrastructure was at that time progressing as well. And one thing you'll notice is if you think about it, the EPA was instantiated in 1972 in its current form. All of this happened sometime before then, so there is a little bit of history to consider about, well, when did we first start dealing with the waste that we're putting into water? How are we approaching that? What was our initial motivation? So we'll talk a little bit about that as well. Overall, we don't want wastewater to go into the environment. We don't want to deal with it or handle it. Got a bunch of just photos, kind of a random grouping, but some illicit gold mining, and the mercury they're using to kind of amalgamate the gold that they're extracting is just basically discharged into the environment. A few pictures from Nicaragua here. Some of these not from my trip a week and a half ago, but some of them actually are. We've got open discharge of wastewater. There's some progress in putting in sewer systems, but in the moment, there's actually just wastewater flowing. Pretty terrible situation. Whereas in some cases you have wastewater treatment lagoons. This is a pig farm, and they've got some treatment. In the wet season, it kind of overflows some, so also not ideal. On the other end of the spectrum, earlier this year, I was flying to do kind of a research collaboration with some French colleagues, and I spotted this from the airplane, and I thought to myself, that must be Paris's wastewater treatment plant. And sure enough, it's probably the biggest in France. I was texting my wastewater buddy as soon as I landed. I was like, hey, look what I found. And yeah, we're just kind of ridiculous that way. And he has a project going on there, and he told me all about it. But you can see, if you look closely, these little circles, these would probably be little clarifiers for their treatment. They also have this really cool wastewater treatment truck there that is designed specifically with different tertiary treatments. We're not going to talk too much about it, but these would be like, an advanced membrane or an advanced oxidation process with a disinfection. And you can bring this truck to a standard wastewater treatment plant and then produce water that is extra clean for reuse purposes. So you can pull up to a wastewater treatment facility and then fill up a large tank that can be used for irrigation. You can fill up a different tank with a different process that could be used for cleaning city streets, based on the needs in terms of what kind of contaminants are still there. So kind of a complete range here of wastewater technologies or lack thereof. So many reasons we care about it. We've seen this slide before, kind of the scope of our engineered water cycle. And we've talked a lot about the incoming section where we're going to treat for drinking. And now we're going to begin talking about the wastewater, a bit of collection perhaps, and also obviously the treatment, and also what happens as we leave the wastewater treatment system. So kind of that's the next tasks, and we will see a lot of the skills with the mass balances will come back and be relevant yet again. So a typical wastewater treatment plant, obviously there are different designs, but this would be a very typical conventional treatment plant. We will categorize it into primary and secondary treatment. And if there's something else in addition to that, we would consider that a tertiary treatment. Things like that specialized treatment truck or some fancy nutrient removal to get water extra clean for a particular environment would be a tertiary treatment. But the primary treatment would simply be physical removal of debris, of stuff in the water by screening and then sedimentation. So that'll take care of some pollutants, some of the largest, the most obvious things. Will provide some treatment. It's certainly better than nothing. It typically is quite cheap. In some situations, for example, we talked about Flint last time. Well, nearby in Detroit, they have an enormous wastewater treatment plant. Probably, I think it's the biggest in the country, and probably close to in the world. They treat all of the metropolitan Detroit area plus a lot of the surrounding. And what happens for them is they get a lot of snow melt every year. And so seasonally, they have, seasonally and historically, they've had a whole lot of drainage from all these catchments, snow melting in the streets. They used to have that piped into their collection system. So these days, and they have been working towards removing this connection between storm sewers and the municipal systems. And to an extent, that's a great thing to do when possible. In other cases, well, in all cases, you're going to end up with some infiltration. If you have a lot of stormwater, it'll find its way into the sewer systems, at least to an extent. But there's a lot of effort to avoid this, because if you do have a flooding event, you could overflow your wastewater, or simply in your commingled sewer systems, wastewater flooding so stormwater could cause flooding such that your wastewater is coming out of the sewers if it's flooding that bad. So we don't want that. Nationally, we've had these combined sewer overflows have been an issue. So there is an entire program to separate storm systems. So now we have municipal separated storm sewer systems. Acronyms and things all for that. At any rate, Detroit would have, and I think they've improved the infrastructure, but they had the capacity to discharge something like 1.4 billion gallons per day of wastewater that went through primary and secondary treatment. But for the cases where they had excessive flooding, and it's fortunately a little bit diluted, so it's cleaner water, kind of. For the extra capacity and the crazy snowmelt season, they could go up to, I think it was 2.2 billion gallons per day, and the remaining extra was only passing through primary treatment. So that's not typical, that's not ideal, but that was, at least for a time, when I learned about it, and toward their facility, that was the situation. So at any rate, primary treatment, it's very basic, better than nothing, but it's not doing a whole lot. So then we take secondary treatment, which is our biological system. And a biological system really involves having a way to promote bacteria to grow. Like I said earlier, we want to do that, even though we don't want bacteria eventually in our discharge. We want bacteria to grow abundantly because they do a great job of eating stuff, eating very small stuff, making that stuff become larger biomass that we can handle more easily. If you remember at the very beginning of class this semester, I said we have stuff and some other stuff, right? Well, bacteria do a great job grabbing it and forming bigger piles that we can remove. So that's going to be our secondary treatment. That's going to entail almost always an aerated chamber. This would sometimes be called waste activated sludge, or WAS. We're activating the waste with oxygen. It's a sludgy mixture because we've got a lot of bacteria growing and whatever other waste is in there. And this is allowing aerobic bacteria a great opportunity to munch on bacteria food, which could be waste grease we dumped down the drain, could be just all the organics from our excrement and all the waste products. Whatever is in there that could be biodegraded is being consumed and used as food for the bacteria. Sometimes we will also do anaerobic, and perhaps if we have both, we might consider both of those together, the secondary treatment steps. But the basic thing would be aeration. And if we're discharging to a surface, we always want to have aeration at least once in the system to make sure we're discharging water that is not going to demand a bunch of oxygen. We'll talk about oxygen demand quite a bit. If there's a lot of food that bacteria in the environment could eat, and we discharge that, then bacteria in the environment will do the same process. And they'll demand the oxygen from the water, and then the fish don't get any oxygen because it's all gone. So we don't want that. So we're always going to have some aeration step, often calling that our waste-activated sludge. So once we grow all those bacteria, we've got to catch them. That's where our secondary sedimentation chamber comes in. And we're going to accumulate in these, and these sedimentation chambers for wastewater are just by convention more often called clarifiers. So it is the same thing as the sedimentation basins we've been talking about earlier in class, but now we typically call them clarifiers. These usually don't need so much help in terms of adding some sort of coagulant and stuff. Certainly you could, but conventionally the bacteria have grown enough, they're kind of doing their own coagulation type of process. We just usually let them go through that way. It removes almost everything, and we disinfect to catch any of the remaining. We don't need it to be quite as pure as drinking water for obvious reasons, so we don't hold it to the same exact standard, but we will usually disinfect and then discharge. Depending on what kind of water is receiving, we might need to remove the chlorine. In some cases, it's not really necessary. Depending on how the mixing zone occurs, is the chlorine going to be some threat to the environment? Of course, we don't always have to use chlorine either. We could use UV. An example here would be our South Baton Rouge wastewater treatment plant discharges chlorinated wastewater, but it's heading straight into the Mississippi River, and the flow differential there is such that it's getting so diluted that we couldn't harm a fish if we tried with the chlorine adding to it. And so we don't actually have a chlorine discharge limit in that scenario. Okay, so that's kind of secondary treatment, and you'll notice another component here for both of these is to capture the sludge and whatever particles, and we will usually collect those, and well, we always collect them and then process them in some way, and that's an opportunity that we could generate fertilizer. If we treat it properly, we can create biosolids that may be able to be used for a kind of a beneficial reuse. It's also possible that we just landfill it, and so we'll just be filling up trucks. So we'll have to take this sludge, dewater it, and then send it along, is typically the process. So that's our typical wastewater treatment plant, and we're going to take a look at how and why different contaminants are treated here and how to track those so we could consider how to design wastewater treatment. So regarding regulations, there's a few ways to look at it. One would be, okay, how is this water going to impact what we call the receiving water? If we discharge to the Mississippi, there are certain things that we have to consider. If we discharge to a creek nearby, there are certain things we have to consider. If we discharge to a ditch that is only has water in it during kind of the rainier part of the year, and now our wastewater is basically now the stream, we kind of have to treat that as a water body because we're making it in some sense. So things can get pretty complicated. There's a lot of debate even today about what is considered the waters of the United States for regulatory purposes. Does the irrigation channel along a farm that some farmers have created to water their crops and to fertilize their crops, does that count because we have lots and lots of nutrients in there? Or how do we navigate that? Because maybe we shouldn't count it on the farm itself, but then it might run off, and then you have high amount of nutrients way beyond any discharge permit that we'd normally have going into a water body that we care about for these nutrients. So it can be complicated. It can be a lot there, and we'll talk a little more about that. So EPA delegates typically the regulatory authority to each state to kind of navigate what's going on, what does your body of water need, and who's enforcing this, who's dealing with this. Last time I checked, I think there was only 2 or 3 states that did not accept ownership of this this task, and so the EPA itself is doing that for a couple states. And I think for technically tribes and territories could also form their own DEQ type of a situation, Department of Environmental Quality here in Louisiana. I don't think any of them have. So it's the EPA or it's delegated. Now, the surface water discharge wastewater permitting system is called the NPDES, the National Pollutant Discharge Elimination System. I worked briefly as a permit writer for this, so that's where some of the content today is coming from. This is while I was in Michigan. I told you about that last time. And the initial aim was to reduce and eventually eliminate all discharges of pollutants to surface waters. That's a great aim, but to eliminate everything would be perhaps not possible, especially if you consider that temperature could be considered a pollutant. And does that mean we have to, chill or warm our water exactly to be what's there already? In some cases, we might be discharging water that is cleaner than the receiving water. That could disrupt the ecosystem. So are we saying that the absence of something would be a contaminant? It can kind of get a little crazy, and it turns out that eliminating completely is never going to be practical. So instead, we do to the best possible. We'll see the text of that law as it developed in a few minutes, in order to protect the intended use of a water. So for example, lakes, we tend to perceive as we want to be able to use them for possible source of drinking water, for recreation, for fishing, boating, all of these things. We want to protect those intended uses for anybody that might want to use it. We also likely want to preserve the natural ecosystems there as well. So one intended use would simply be enjoying nature, going on a hike and enjoying a lake that has its natural ecology, right? That would also fall under the intended uses. So as long as we're protective of that, then perhaps it's okay to discharge some pollution, right? And you can kind of start feeling this tension and balance between, okay, we don't want to pollute our environment, but we do want to be able to make stuff and have some industry and disrupt the environment. If you think of our building right here, we've disrupted the environment to have this building. We decide we would like a ceiling here and a floor and air conditioning and all that. And so we're going to destroy some of the environment, but generally protect it. So we have nice trees out there and all that. So we're going to have that balance. And another thing you might not consider at first when you think about permits and about wastewater regulation is another thing we want to do with them is actually to protect industries. Maybe I mentioned this at the start of our class, but essentially we can protect industries from lawsuits if we provide them a way to obtain a permit, and then they are not the ones responsible to do the study to prove that they didn't harm you or harm me or whoever's downstream. So if the EPA can establish, hey, if you follow this protocol, we're going to permit you to discharge X amount, kind of like we get a license to drive. We're permitted to drive, but that license could be revoked if we misbehave. These permits to discharge wastewater are a license to discharge wastewater as long as you meet some regulations, right? As long as you keep to these standards. So if a company or an industry had to figure out for itself and prove legally, scientifically, that no, they're not harming anybody with what they're discharging, if that burden was on them, then each and every one of them, including every dry cleaner, would have to have the capacity to do the studies to test and make sure that they're not contaminating the groundwater in a way that's harming anybody or the surface water, right? So if we add this permitting process and permit legally discharge of wastewater, meeting certain regulations, we actually allow industries to operate. It's taking a huge burden off of them, and then people will sue the EPA instead of the industry if somebody did get hurt, right? Because the EPA allowed it, or the DEQ or whoever, they're the ones that end up facing the lawsuit because they didn't properly, insist on proper protection. So it's not perfect, but there's a lot of stuff going into that, and in a backward-seeming way, the regulatory framework can actually help industry. So if perhaps your perspective might have been, all regulation is bad for industry, you'd be a little off there. Of course, you can go too far. It could be too cumbersome to navigate. And this is a balance that anybody working in this field is going to have to navigate, right? How do we make sure we're protective? How do we make sure we're taking appropriate precautions and not allowing any misuse of the environment, any risking of the public or any of our natural water systems or other ecosystems? But how do we do that in a way that's favorable for everybody, right? That's simple, that's not too time-consuming or whatever. Now, I will say that these permits also have a cost. So I mentioned the Detroit water treatment plant. For the bigger permits like that, they are paying millions of dollars per year for their permits. So that permitting process also funds the systems in place to regulate them. So a simple permit, like stormwater permit for like an auto repair shop, they have to have a grease catch for any runoff, so they're not adding grease when it rains to the natural system. That type of permit is pretty cheap. It's pretty simple, but it's some fee. For the big discharges, there's usually quite a hefty fine accordingly to scale. So it has some cost, but it's supporting the operation of these regulatory frameworks. Okay, so that's kind of a big picture of how we structure our permitting system. We'll come back to look at a little more of the permitting details. I've got a workbook that I had from 10 years ago we can look at as well. So types of pollutants, mentioned a few of these before. One of the primary ones, the most obvious one perhaps, is biological oxygen demand. I say obvious. When I say it that way, when I say biological oxygen demand, that doesn't sound very obvious, and it's a little not intuitive in terms of what it means, but it's going to be obvious if you have a fish kill when there's no oxygen for the fish, right? If you discharge water with a lot of stuff that microbes will eat, suddenly they eat a bunch and they take all the oxygen out of the water, and you have a big problem. It smells bad, it kills the fish and wildlife. It's very obvious in that sense. So BOD, as we call it, this is a measurement of how much oxygen the food stuff will demand when bacteria eat it. So anytime we eat something, we have some respiration, we use it for energy, and we breathe out. We breathe in oxygen and out CO2. In fact, funny thought here for you, that any way we gain or lose weight is going to not be necessarily what we excrete, but more like what we breathe, because it's energy that we are consuming is carbon. We're going to be oxidizing carbon through respiration to go from some organic carbon that we ate, like sugars or fats or whatever, and we're going to exhale CO2, having made use of the energy from that bond breaking and the chemistry there. So when we do that, we are exhaling carbon. Bacteria will be doing the same thing. For every sugar molecule or every other molecule, whatever molecule they're eating, they're oxidizing, converting oxygen to CO2. They're getting energy, maybe they're building cells with it. Those are the processes. So every X amount of food, they're going to demand Y amount of oxygen. Okay, they will have some proportion there. So the more waste in the water, the more oxygen the bacteria will demand once they're able to eat it. So that's why we add in lots and lots of bubbles for our wastewater. So it'd be a waste-activated sludge system we see here. We add a bunch of air so that we can take care of that in our engineered system so it doesn't happen in our natural system, right? So this BOD is typically milligrams of oxygen for every liter of water. Now, if we said we had 10 milligrams of oxygen demand per liter, and our natural water maybe has 8 milligrams of oxygen per liter in it, then we will consume all of the oxygen if we had just had 1 liter and we had it sealed and we just let the bacteria go to town, right? It would deplete all the oxygen and it could consume a little more if it had the opportunity. So, and that's actually exactly how we measure it. We'll go through some of the math. It's pretty simple. But that's what BOD is. That's what our biological oxygen demand is. It is a measurement of bacteria food. And we're measuring it based on how much they're breathing. Because when they do so, when they eat, this is essentially the process. This could be anything from sugars to fats, just kind of any organic matter that looks like food to a microbe. So we've got oxygen taken in, plus this food, and we're getting CO2 and bacteria cells from it, and it's this oxygen demand that the bacteria are demanding from the water that we are counting with BOD. Okay, does that make sense? All right, so that's a really good starting point to understand what wastewater treatment is all about. If we can handle that and nothing else, we've done something good. That's important. It'll also help prevent it from being too stinky. Now, if you go to a wastewater treatment plant that's operating well and it has a nice aerated system, you would expect it to smell terribly because it's wastewater. Actually, if it is operating well and everything is aerobic, it actually just smells like slightly stinky dirt. It actually doesn't smell too bad. When you have anaerobic processes, which sometimes is on purpose, that's when you get the really bad smelling stuff. So this will also improve the smell, which is kind of our body's indicator. Is something rotting? Is it something fermenting? Is something bad here? If we give it plenty of oxygen, we'll notice that too. Okay, so in addition to BOD, we have other, and this whole slide is conventional pollutants. They are kind of more modern or more like things we started caring about once we got the conventional things taken care of, but this is just how we call them. Next one would be total suspended solids. So any solid material that is suspended in the water, we want to get rid of it. So this would be described as TSS, and we'll usually do some sort of weighing, filter it a little bit, and weigh out, okay, how many solids, what mass of solids we have in every liter. So this could be the bacteria that we're growing. This could be random particles of stuff in the wastewater. This could be anything that is a solid that is kind of floating around. So total suspended solids. And we could measure that in natural systems as well, right? Sometimes we have a rain event and then the river gets really muddy. Well, there's a lot of suspended solids, at least for a time. And you know, if you think about it, most natural environments don't have a ton of total suspended solids, at least not all the time, right? There's usually some disruption, maybe a rain event or something that would cause that. pH would be another one, pretty obvious. Natural environments tend to have slightly basic, or at least close to neutral pHs. So if we're discharging something very acidic, we've got a problem. And we could, that could be very hazardous to an ecosystem. Next up would be fecal coliforms. This would be an indicator bacteria for fecal contamination. So we call them fecal coliforms. The way we measure them typically is we would just say any type of bacteria that can grow under these certain conditions, maybe with some media on a petri dish, when we incubate it at temperature that is typical of a warm-blooded gut. Doesn't necessarily mean they are fecally related, but there's a good chance. So we count that we make that kind of a count, and we say, all right, well, we have this number of these microbes per liter, and so we have some concern. Last, we would have oil and grease. We've already talked a little bit about this and why we care about this, but basically we don't want our rivers and lakes to catch on fire. A little bit obvious, but if we didn't treat for oil and grease, turns out that does happen. As we saw before, this is the Cuyahoga River, and then we saw also this, this one was not a wastewater related, but this was our a broken pipeline. Okay, and a couple links to each of those here, and I think I've got maybe the excerpt to the Cuyahoga River as well. So other types of pollutants would be toxics, and then a catch-all non-conventional. It's just how it's described, it's how we label them. So we've got conventional, non-conventional, and toxics. Toxics are pretty obvious. There are things that are toxic, specifically heavy metals and specific organic compounds. We actually have a list of priority compounds that we are concerned about. So, you know, things that we know are particularly poisonous or are particular byproducts of industries that we know are a problem. That doesn't mean there are other toxics that aren't on the list. So there are cases where the EPA will review every so often to add things to that priority list. And if there is a case where a new industry is producing something that's not on the list and it is toxic, of course that's going to be regulated, but navigating to get to that point is part of the reason why sometimes each permit is individual and may take some time to get settled on what exactly is the permit requirements for a particular industry. Okay, and we'll take a look at that manual to see one of those lists in a few minutes. Non-conventional would be kind of everything else. I mentioned chlorine already. I guess maybe you could consider it toxic. It's not very toxic, at least not in high quantities. Ammonia the same. And so sometimes those are okay. The Mississippi River, for example, probably has so much, at least down here, has so much what we call assimilation capacity, so much volume of water that ammonia, which is naturally occurring, it's not going to disrupt the ecosystem at all if we discharge a fair bit of it from a wastewater treatment plant. Now, if we discharge that into a smaller stream or river, it could be quite disruptive because ammonia is toxic at several milligrams per liter. So if we discharged 5 milligrams per liter of ammonia and most of the creek is now, becomes 3 milligrams per liter because most of the creek is our wastewater, suddenly that kills everything. If I have those numbers right. I think it's 1.5 is where it starts, we start getting something, but don't quote me on that. Not remembering at the moment. Either one of these could cause a problem, or maybe it's totally fine if there's enough assimilation capacity. So that's why we're not necessarily going to call them toxic. Chlorine will react with something and kind of decay and go away. That'll be fine. Ammonia, biological processes will convert that or consume it. You'll get nitrite, then nitrate. each of those, these are nutrients, but they're not necessarily like a bad toxic, okay? So there are issues. Phosphorus is another nutrient, so we have all these other categories that we might be concerned about. If we put in a bunch of nutrients, we can cause perhaps what we call eutrophication, lots of algae growth. We could have so much algae growth that then it kind of blocks the sunlight from going deeper into the water, and then it's only the top that gets photosynthesis. Everything else starts going anoxic, and then at night, all those algae are going to start doing respiration instead of photosynthesis, so depletes the oxygen because there was just a bloom of algae. That's eutrophication. So there are reasons we're concerned about these things that are not exactly BOD, that are not exactly toxic, just other stuff. So that's our non-conventionals that we sometimes care about. Okay, so I want to talk about primary treatment before we, well, actually, you know what? We'll go ahead and do this. It'll be a nice break point. So primary treatment, to begin our treatment train, is the stuff that we want to stop large particles mostly, or objects of any sort. And so anything that can be stopped by physical screening and simple sedimentation is what we want to get rid of. This does remove some BOD, but it's definitely not a lot. It may be 20 to 30%, something like that. Not exactly sure. It's not going to be significant enough to say, okay, this is a big part of it. It's just something kind of we have to do for the plumbing and just to make sure that everything's good downstream. And it's always useful to get rid of whatever gravity we can. Now, I have a funny video that the first time I was teaching about this popped up. I don't even use Facebook anymore, but it popped up way back when. And so I'm going to share this. Need to make sure I get the sound going for you because it's a little bit of commentary and it's kind of hilarious. Okay, so anybody ever heard of a fatberg? Yeah, have I shown some of you this before, or just heard it somewhere else? Okay. Moral of the story here is flushable wipes are not so flushable because they don't degrade, they don't dissolve on contact with water like our toilet paper does. So yeah, I'll let this tell you. Oh, hang on. I'm sorry, we have to have the sound. I insist. I know, I'm hiding also my camera so that I can actually see the button. Maybe. Still practicing. Okay.
So-called flushable wipes getting stuck in the sewer system.
I have never seen one dissolve.
They have to remove them on a daily basis.
15 tons. Anybody want a job? I hear that it pays well. Hazard pay and all. All right. So that's why we don't flush flushable wipes. They're not so flushable. For some time, I had ew is right. For some time, I had the thought that how could you see something dissolve? That's such a silly comment. The guy makes it. But at the same time, I bet if you took a piece of toilet paper, you could see that half of it dissolved and half of it was still remaining if it was dry, right? So I think the wastewater operators probably know best here. And in fact, I remember touring Detroit's wastewater treatment plant, that massive one that I told you about. It was a bit gnarly, not super clean, and each of those things that they said don't flush, you could definitely find around debris scattered. And it was kind of gross. So there you go. Career options if you want good pay and can't find anything else. Hazard pay in the sewers. keep our sanitation systems going. Okay, so the first step to try to catch anything like that, before we do any sedimentation, we typically actually have some sort of a bar rack or screen and perhaps a grit chamber. And actually, we can often automate these things. So I have another video here, and this is just some advertisement from some company. So I just assume that it's fine that I'm sharing it, and they'll just appreciate that it's free advertising, I guess. That's my take anyway. If I could just skip forward a little. I don't even know if there is any important sound in this one. But what you see is they have it set up so that water's flowing, you've got this little screening rack, and then it'll automatically kind of scrape off the stuff, draw it up, dump it into a dumpster, and just kind of have this nice automated process to do that. And I have seen a few different versions of these. They are, Detroit had a whole room full of this type of operation with little dumpsters right next to them. And again, it was a pretty messy process because sometimes things don't fall quite into the dumpster, or, you know, just gross stuff laying around everywhere, and it stinks. But ideally, it would take these little buckets or whatever as it's going and eventually deposit it into a container for landfilling. So that would be kind of a part of the primary treatment. From here, maybe we go through one more step. They kind of have little barrel tumblers, almost like a dryer, where water can go through and it'll collect like large sand or tiny pebble type size stuff. Those types of steps are really nice to help prevent any damage to plumbing and your pumps that the water will go through next. So that all these pieces are pretty important, even if it's not, you know, doesn't do anything super fancy. Of course, after these, you know, grit chambers or screening, then we'll go into the first clarifier, the first sedimentation basin, let gravity do what it can, and move on from there. Okay, so I have this this permit writer's workbook, and let me tell you, it's working in NPDES can be pretty interesting, so I don't want to discourage anybody from going there, but having a week-long training session was not the most exciting thing in the world. I did get to go to Chicago, but then it was like 8 hours a day, and unfortunately the speakers were very monotonous, and so we were talking about wastewater regulations with about this tone about what happens in the Cuyahoga River. And okay, sorry, I'm falling asleep here. So hopefully we can just do a really quick version that's a little more interesting, get the highlights, so you don't have to go through that too. And that's not being very charitable, but it was kind of a funny experience. Needless to say, I was also in a position where I just finished grad school, and then I got any job that I could find. Back then, jobs were pretty scarce for me, and it was kind of like I was shoveling paperwork because it was very entry level. Wasn't using any of the skills that I had really. Anyway, so here I am a few years later. So I'm going to actually use their slides, a few of them, to kind of highlight a few of the pieces of history might find interesting. Feel free to stop me if you've got some questions at all. Early on, I mentioned at the start of today's class that, well, there's some history, and we didn't have the EPA back in 1900, so what did we do? Even in England, we talked about John Snow last time, or some, a couple weeks ago, and we were saying, well, they started recognizing they have to do something with their water, wastewater. So over time in the U.S., probably the first thing that really touched on our discharges to rivers was the 1899 Rivers and Harbors Act. That was primarily for navigation. So if something was happening that hindered navigation, okay, that's where maybe it would fall. I don't think we were setting rivers on fire yet, but that would certainly be a navigational hazard as well. So if nothing else, we'd catch it there. By 1948, we actually did have some more formalization kind of under the Rivers and Harbors Act that became the Federal Water Pollution Control Act. That was not only navigation, but then human health concerns were being added. 1965 then was the Water Quality Act. That was requiring standards for interstate waters. So one state was complaining about the bad water quality from the other. I can only imagine Louisiana had to be one of them, receiving water from everybody else, the Mississippi, right? Of course, there's the Cuyahoga River. That quote, I think I shared this in the past, but some river, chocolatey brown, oily, bubbling with subsurface gases, oozes rather than flows. Anyone that falls into it does not drown. The citizens joked grimly, he decays. Okay. And this is 1952, and there's kind of a dry note here. It says, the Federal Water Pollution Control Administration dryly notes the lower Cuyahoga has no visible signs of life, not even low forms such as leeches, sludge worms that usually thrive on waste. It is also literally a fire hazard. Okay, so that brings us forward a little bit in the first rendition of the EPA and what was called the Refuse Act Permit Program, RAPP. That doesn't sound familiar because it was struck down. But that was in 1970, and this was established by an executive order. Then essentially Congress began to fashion a program that would be legal and substantial. So just as a, wherever you fall in interest or disinterest in politics or whatever, one thing to note is we've always had this kind of stuff happening, and eventually the concept, I think, is that we can make some progress towards whatever challenges we have. Sometimes that might take somebody to try something, and then it's, okay, that wasn't legal, let's not do that. But there's maybe motivation then to do something that Congress would pass as law. So was the situation with the EPA. And so by 1972, we kind of have what is our current program. It's established by Congress. That would be the Federal Water Pollution Control Act amendments. And so that's the basis of what we have today with the permitting system for wastewater discharge. A little later, we got the Clean Water Act, 1977. This was for those priority pollutants we'll take a look at and kind of establish some general effluent guidelines of, okay, you may discharge this, you may not discharge that. What are the standard guidelines? Then we have the Water Quality Act in 1987, and that one focused on water quality-based limits, so and then added stormwater to the types of things we were regulating. So water quality-based limits are for the cases I've mentioned where we need to maintain a specific water quality for a particular body of water. We have some bodies of water in our nation that are particularly high quality or pure, pristine. A couple of the Great Lakes, I think Lake Superior, for example, is one of these designated as very pristine or high quality. So whatever wastewater we discharge there, we're tasking ourselves with meeting a higher standard to maintain that better water quality. Okay. Mentioned this already, but it'll be nice to see exactly the text as it was. So initially, in 1972, the objective was to restore and maintain the chemical, physical, and biological integrity of the nation's waters. And that sounds great, right? I think probably everybody would agree with that to any extent possible. Restore and maintain chemical, physical, biological integrity of the waters, right? That kind of covers almost everything. But it also doesn't mean we can't have some disruption if we decide that we really would like to have some industry and maybe it's going to discharge just a little bit of BOD and we can treat it so that it's not a lot of BOD, and we can regulate it so that it's not going to significantly alter the receiving water, okay. We can maintain the biological integrity, right? We're not going to cause an algae bloom. We're not going to cause eutrophication or complete starvation of oxygen. We can maintain that integrity. And we need the physical and chemical as well, because things like pH, which would then affect biological, or simply just changing the entire waterway by adding a bunch of sand, right? That would also just be disruptive. Okay, then the national goals and policies included, and here's the kind of the fun part, to eliminate the discharge of pollutants, just all pollutants, to navigable waters by 1985. We still discharge some pollutants today, so that didn't happen. Like I said, that was not necessarily realistic, but that was the goal. As an interim goal to achieve by July 1st, 1983, wherever attainable, a level of water that provides for the protection and propagation of fish, shellfish, wildlife, and provides for the recreation in and on the water. And lastly, to prohibit the discharge of toxic pollutants in toxic amounts. So this one here, this middle piece, I think is really important. I think that's the crux of our system today, and eventually we recognized. And we don't always achieve this. There are some cases where we're not achieving it, but that's our aim, to always achieve that. Wherever attainable, a level that achieves XYZ, right? All these intended uses. So that's where the intended use comes from, is that particular goal. Okay, moving on, we have this NPDES permitting system. There is a parallel one for groundwater. I don't know as much about that. That wasn't where I was working, but there was a similar system aimed at protecting our groundwater resources with similar treatments required, because you can potentially discharge water to the ground. The permits, just a few general topical things. They can only be up to 5 years, and realistically, any of the big ones or complicated ones are renewed every year and reevaluated every year. You can have, in some cases, you can have technological based, where we know that if you had, let's say, common petroleum products, that activated carbon filters are the way to go. And so we can prescribe, okay, if this is your industry, you've got a groundwater cleanup that was contaminated by a gas station, for sure you're using activated carbon, and this is how you're doing it. You have some option of saying two activation column tanks. Here's the typical operation. You can design it exactly how you want, but you're using carbon, a technology-based treatment. And we know that it works. We know it works so well, and that we know that these are the contaminants. There we go. So there are some cases where a technology is prescribed instead of an effluent limit. If that technology is known to work exactly that well, we can just say, as long as you're meeting these technological requirements, this can be your wastewater treatment, and you're good. So occasionally we use technology, like a technology-driven. In all cases, we have some compliance deadlines, and how are you reporting this? And if you're not living up to your permits, and you didn't want the permitting authority to come and check if you're not cooperating, the National Guard shows up at your doorstep and points a gun at you, says, "Open up." Basically, that's what happens. So it is a federal legal issue. So people will either comply or they'll be in big trouble, basically. Now, sometimes trouble just happens because you're trying to comply and you failed. Okay, so maybe there's violations and fees kind of thing. And then you have to hire people like us, consultants, to help fix the problem, right? To engineer the wastewater properly, wastewater treatment. Okay, in 1976, that's where this priority pollutants list came about. 65 categories, 129 pollutants. We'll scroll down and see a list for that in a moment. And that at the same time, that technology-based effluents were kind of established for certain industries. Sorry. Okay, more legal stuff happened. One thing I'll note here is the pre-treatment program. So sometimes an industry would like to discharge their wastewater, get rid of it, not have to deal with it, and they think to themselves, okay, well, what about the sewer system? They do wastewater. Why don't we just discharge our wastewater to the sewer? Sometimes that's fine, as long as you're paying the sewer system operators to treat the waste. Sometimes that's not fine because suddenly you're doing something so toxic that the bacteria in our wastewater treatment plant that's doing like this, the normal municipal sewage, is if you kill all those bacteria, suddenly, well, what happened to our bacteria that we're using here if they all die because something really toxic came in? There's no more wastewater treatment. The best you're getting is sedimentation. So we have to have pre-treatment to prevent that. And so, you know, probably learned the hard way, but 1977, that was part of what was added is, okay, well, if we have an industry that wants to discharge to municipal treatment, maybe there's some pre-treatment programs that we could put in to make sure that we're not destroying our normal wastewater treatment in an effort to do that. Okay, a little more, if you're curious, I'm going to start skipping a little faster, but stormwater stuff in 1987, and also sludge management programs. This is when we started to think about how can we make use of biosolids. A little more stuff we've talked about. What is a permit? People don't have a right to contaminate the environment, but we provide this permit federally to do so. So it is a federal offense if you are discharging wastewater illicitly to waters of the United States. Okay, I mentioned the runoff stuff for agriculture. I think that is still back and forth a little bit over the past 5 to 10 years, even to date. What is waters of the United States? So you might see some controversy about that. What is a pollutant? Does it have to come out of one spot? Can it be, is it a point source or is it non-point source? Here's this classification that we talked about, each one of those today. Again, more debate about what is the waters of the United States. A lot of the stuff that happens in the world of environmental regulation is often driven by legal matters, right? So there's a lot of court cases and things like that to take a look at. Mentioned groundwater. There is a permitting system for that. And then what about treatment ponds or lagoons? Well, we'd be in pretty big trouble if the body of water that we made to treat the wastewater is considered a water of the United States, so we exempt those. So if we have a treatment pond, it is not a natural pond. Sometimes some wildlife might get in there and maybe even be fine living in there, but that's not the design, so we're not considering it that way. So at the end of the day, after all these treatment processes have been put in, at least for the Cuyahoga, it's good news. We've made a lot of progress over the years. I don't think we've seen any rivers catch on fire in our lifetimes. So good news. Some of this is certainly working. And this is the little testimony. Did we already read this? Did I read this to you guys? Okay, I'm sorry. I keep feeling like I did. I think I dropped in on EVEG 1050 and gave them like a little snippet. So here's this Cuyahoga River revisited. Did we watch the fire on the river at the start of class? No? Okay, I'll come back to that too. I'm sorry. I'm glossing over it because I was feeling like I've already talked about it. Okay, so this is the river that we saw on fire over. Let me get back to it. See what I'm doing. Right here. So this river, that's the Cuyahoga River. So to back up to this, because I blazed through it, there's a layer of grease on the water here. And that's kind of what happens when you have a lot of industries discharging oil and grease. Well, grease floats, and you get a layer of grease on the surface of the water, add some sort of ignition source, and suddenly your river's on fire. Not a good situation. And what we see here is this boat has caught on fire, and some firefighting boat or maybe on the shore is trying to help put that out, I guess. But any of you ever dealt with a grease fire? Okay. What do you not do to a grease fire? Exactly. You don't ever put water on it because, well, grease floats, and if you put water on top of grease that's on fire, what happens is that water wants to go underneath. Now that it's underneath, what temperature does water boil at? 100 Celsius to 12 Fahrenheit. Well, what temperature does oil burn at? Hotter than that. So what happens then is you have water that's getting way hotter than it wants to be, and it will evaporate in short order and turn into gas in an explosive sort of manner and spray your burning grease everywhere in the room. So you don't put water on a grease fire to put it out. So how do you put out a river that's on fire, a grease fire? I think the answer is you probably don't. For a grease fire at home, if you have like a blanket type of thing, you can smother it, or something like a bunch of dirt to smother it, cover it, remove it from the source of heat. Yeah, do what you can. Don't put water on it, right? So this case is quite crazy, quite difficult to deal with. This was, I think, the Moscow River had a pipe burst at some point like 10, 15 years ago. While I'm talking about it, we'll just pull that up so we can show you. Just to get a feel for what this would look like. So you can just imagine that just as your river was a bit dirty and suddenly that was happening. Now, of course, this is a little different, right? This is a pipeline burst, but not what you normally think of as consequences of not treating your wastewater. Okay, so anyway, coming back to that story, I'm sorry I skipped over it by mistake. That river was one that was described as such. And so I'm going to read this little snippet because even back in 2009, we were doing a little better by then. So the first time Gene Roberts fell into the Cuyahoga River in 1963, he worried he might die. Mr. Roberts smelled so bad that his friends ran to stay upwind of him. Recently, he returned to the river carrying his fly fishing rod. In 20 minutes, he caught 6 smallmouth bass. It's a miracle, he said at 58. The river has come back to life. And smallmouth bass, by the way, are kind of notorious for wanting clean, lots of oxygen in the water. So today, the Cuyahoga River is home to more than 60 species of fish, says Jim White, some guy doing the River Community Planning Organization. Beavers, blue herons, and bald eagles nest along the river's banks. Okay, so great improvement, great success story here. We can get into the water quality data of how many rivers and water streams that have been assessed are meeting our criteria of impaired versus good versus threatened. In terms of water quality, we could look at this from lakes or rivers, different things and why they are impaired, pathogens being one of them. Okay, some of those can be natural, some of those can be, many of them human-sourced. Sediment, nutrients, mercury, organic enrichment or oxygen depletion, some chemicals, so polychlorinated biphenyls, metals, temperature. So you can see all this list of ways in which we might quantify how many of our waters are impaired and in what ways. So feel free to take a look closer here. I'm sure there is more data today. Here's that list I was wanting to show you. Priority pollutants. Some of these you might recognize. Some of these you might have never heard of. So benzene's on here, chlorophenols, DDT, toluene, pyrene. We also have some inorganics, arsenic, cadmium, chromium, copper, cyanide. Big list, okay? And this list is revisited. I think it's probably slightly larger than it was when it on this particular table. So that's chapter 1 of this book, this little Permit Writer's Manual. I put it on our Moodle so you can take a look if you wanted to read a little closer. There are several chapters. I think that's about all I want to cover from it right now. But if any of this is getting you curious and you want to learn more, have at it. And there's a table of contents here. We can see these different chapters or modules. So the scope and framework, the permit types, permit application process, and so on. So I wanted to show you some of that, where I got a fair bit of the material for the background here. So we're pretty much done, but I did want to say two things. One is I reopened the Cryptosporidium quiz till the end of tonight, in case anybody still needed to do that. And a couple other pieces. I posted your last homework, so that'll be available for you. Not really any reason to start it now, but it's up there. And last piece, I had a question. I have one student who's curious about reference management software. So I'm just going to spend 5 minutes showcasing that. This is not really related to this class, but if you ever wanted to write a paper with some references, stick around for the next 5 minutes. If not, you can feel free to exit quietly, but I'm just going to show you real quick what this free software that LSU purchases for you is and how you might use it. So that's the way I'm going to end today for you. This software, it's called EndNote. It is plugged straight into Microsoft Word. So this is the program. I have a few references in here. I'll show you a little bit about how to get references. What you can do with it is if you're typing in Word, you're writing about something fancy science stuff, and you want to maybe spell it right would help too. And you want to put some citation that you have. I've got a question online here, so I'll just answer that. We've not covered any of the material for the upcoming homework yet, so no reason to start it just yet. It's just posted, by the way. Okay, so let's say we're writing some fancy scientific stuff and we want to add in some references. Maybe these three look good, and we insert them. We just click a button, we select them and click a button, and boom, we have references. Maybe I don't like the way that's formatting them. I can go into Word and say, well, let's use a different referencing citation format, and boom, all formatted for us. Let's say, some other stuff we had to talk about, and we need some more references, but we also kind of need one of those other ones too. Well, we can put those in, boom, and it orders them all for us. It puts the numbers properly. It's just super, super, super convenient. And the way to get references into there is also quite convenient. So let's say I wanted to add some new paper that I found. I could go to the library and go to like Scopus and search a database for a scientific article, or maybe I'll just say, write some fancy scientific terms like TiO2 photoanode. I'm sure I'll find a science paper here somewhere. Okay. Sciencey paper. Okay, so here's a paper related to this library that I happen to have up. So anytime I go to a scientific journal article somewhere, it'll vary by publication, or you can just find it all in the same spot within the LSU library, but you'll find some way to cite it, or to share the thing. So I'm going to go ahead and say citation and abstract, and it goes ahead and downloads something straight into my EndNote file. So now, here's my new citation, and I'm just thinking to myself, oh, one more new citation for example. I say, okay, this one's going right there. I put it there, and then I realize, well, you know what? I kind of wanted that to make that statement up here first. Boom. Okay, all done. It's not 100% perfect, and it gets a little annoying occasionally if you really want to get the fine-tuning. Like sometimes the text down here, maybe there's some abbreviations, or you don't want the abbreviations. There's some fussing you can do with it, but as you can see, it'll save you a bunch of time anytime you're doing some technical writing. So I highly encourage you, This is software that you can simply go to LSU's Tigerware. If you don't know about it, check that out. All right, so there you go. Hope that was helpful.